Some people, after seeing the fictitious exhibition Goethe and Urbain painting with ideal colors, have asked, what is so special with ideal colors? I will give you a hint about that. We have to go back to the days of Isaac Newton and his famous experiments with glass prisms, described in the book Optics. Newton proposed that the elongated spectral image he obtained by sending a narrow beam of sunlight through a prism is due to a splitting up of the original beam into a series of different sorts of light, characterized by different refrangibilities as well as different colors. He further showed that if the process is reversed, that is, if all sorts are superimposed to form a collimated beam, the original white light is regained. This supported his thesis that the different sorts of light are, in various proportions, independently present in any flux of light. The question now arises, how can Newton's theory be used to explain the various colors of objects we see around us? Newton suggested, colors in the object are nothing but a disposition to reflect this or that sort of rays more copiously than the rest, which seems reasonable. In other words, the spectral composition of the illumination is modulated by the material it passes through or is reflected from, and by this modulation carries with it information about the chromatic disposition of the object. Let us tentatively study the process using color filters held in the way of a flux of light. By help of a slide projector, we project on a white screen this picture. Mount the prism horizontally in front of the objective and we get an image like this. To the left we have the spectrally separated sorts of light. To the right we have them mixed together into white light. In this case, the light from the lamp in the projector. All this is trivial geometrical optics. I now put a yellow filter from the right, partly in the way of the light flux. You see that it totally absorbs the light in the blue region of the spectrum, but seems totally transparent for the rest. A blue filter absorbs the red and yellow at the opposite end of the spectrum, and a magenta filter strongly absorbs the green region in the middle of the spectrum. It is evident, at least when it comes to strong saturated colors as these, that a relatively broad absorption band is effective at various positions along the ordered series of elementary sorts of light. These observations inspire the following theoretical considerations. Our starting point is a full spectrum containing all sorts of light, here denoted as wavelengths over the visible range 400 to 700 nanometers. Let us start by screening off a big part of it like this. The light flux, where we have removed the violet and blue sorts of light, should look yellow, as we saw in the tentative study. Next, what about the sorts of light we eliminated? Of course, they also together constitute a light flux of a certain color, in this case blue. In the first spectral composition, light is replaced by darkness at all wavelengths up to about 530 nanometers. In the second composition, darkness reigns at all wavelengths above 530 nanometers. The two light fluxes are complementary, in the sense that if you fuse them together, they make white. They are also opposite, one confined to the shortwave side, the other to the longwave side of the visible wavelength window. They do not have any wavelength in common. This is the inherent yellow-blue polarity of the full spectrum. By varying the wavelengths where you make the cut, you produce a whole set of complementary yellow-blue pairs of colors, starting with a dark blue-violet together with lemon yellow, further on to various combinations of blue and yellow, ending up with cyan together with ruby red. They differ in what we can be described as an increasing quality of redness in correlation with increasing darkness. A third step in our tentative investigation was to use a magenta filter. It absorbed light energy in a middle region of the visible spectrum. We can imagine this absorption band moving all over the visible spectral range like this. It then starts like the yellow boundary spectrum, but as you see, it goes over into the magenta case and finally ends up with cyan, complementary to deep red. So, an absorption band passing through the visible window generates a so-called inverted spectrum, from white to white, via yellow, orange, purple, violet, blue, cyan. However, the absorbed light taken by itself would represent a green light, complementary to the purple one. How do we generate that with pigments? It seems we need two absorption bands, one at the long wave end and the other at the short wave end. In reality, you often get this by mixing two pigments, according to the well-known rule, mix yellow and blue to get green. Anyway, to get the closed set of ideal colors, all complementary pairs must be included. By varying the position of the two cuts, you generate a two-dimensional set of colors, including those of the simple boundary spectra as a special case. Via the purples and greens, you get the full circle of hues. Furthermore, depending on the width of the gap, each hue is obtained with various degrees of saturation. Approaching zero width, you get on the one hand Newton's pure wavelength light, before reaching complete darkness. On the complementary side, you end up with a full spectrum, i.e. white light. So black and white are the poles spanning this color system. How can we now mathematically characterize the filter or other material structures that accomplish the described modulation of the full spectrum? We have to measure the intensity of the light passing through the filter, as well as the light intensity we get with a completely translucent plate. The quotient gives us the transmittance coefficient, and this is calculated for a series of positions along the wavelength scale, giving the transmittance as function of wavelength. In case of a color sample, we measure the reflected light of the sample compared with the light reflected from a standard white sample, giving in this case the reflectance as a function of wavelength. The transmittance can be represented graphically like this for the case of a purple ideal filter. Typical for ideal colors is that either the filter is perfectly transparent, which means transmittance equal 1, or it is completely opaque, which is represented by 0. The graph tells us for each sort of light it is either present or not in the emergent light flux. There is no compromise, nothing in between. The system of ideal colors doesn't permit of ambiguity. So, the transmittance curve describes what a glass filter or a reflecting surface does in modulating the original illumination. Observe that it is independent of the spectral energy distribution. Transmittance is a property of the material, independent of the intensity and quality of the illumination. Following this idea, we can draw transmittance diagrams for other ideal filters all around the U circle, like this. And the following summarizes the said mathematically. Let A and B be the wavelengths where we make the cut. Each pair AB with B greater than A defines a color F and its complementary K. The system of ideal colors defined by these formulas is not only closed and unambiguous, but also all-embracing. It can be used to represent the total gamut of possible object colors. This statement needs a bit further elaboration. To begin with, what is then the difference between the theoretical ideal colors and color materials we find in nature? Let us compare the ideal transmittance functions with measured transmittances of ordinarily available color filters. Here, the transmittance functions do not simply switch between 0 and 1. Instead, at each wavelength we have a certain degree of darkening. Because of this, there are infinitely many possible shapes of the transmittance curves. But let us first note some similarities. If you follow the wheel clockwise, starting with yellow, you can describe the change as an absorption band entering from the shortwave side and proceeding through the spectral window. At purple it occupies the middle part, at blue mostly the long-wave side. A second absorption band enters from the short-wave side, delimiting transmission to the central part of the window, thus producing a green filter. A U-circle with ideal colors is built in the same way. The ideal color circle, based on the principle of complementarity, is perfectly symmetric. However, when we are dealing with pigments found in practice, the second absorption band comes quite close and keeps the overall transmission down, making the colors on the blue side considerably darker than on the yellow side of the U-circle, which is a distinguishing property between the yellow and blue sides of the color circle. The inverted spectrum, ranging from yellow via purples to cyan, contains most of the bright colors of flowers, a fact that was pointed out by the chemist Wilhelm Ostwald, criticizing the Newtonian school for its obsession with spectrally pure lights. So, what characterizes pigments that are both colourful and bright? The issue was considered by the physicist Erwin Schrödinger. In his younger days, at the University of Vienna, he had colleagues lecturing in colour theory and doing research into the properties of artists' pigments. He set himself the task to find out theoretically what reflectance would give the best, brightest colour of a given hue and saturation. He based his considerations on the young Helmholtz assumption of 3 types of retinal receptors with different spectral sensitivities. In 1920, he published a paper where he shows that ideal colors are the answer to the question. Let me remind you of the definition of ideal colors. 1. In no region of the spectrum do they have a reflectance value other than 0 or 1. 2. The reflectance undergoes change at most at 2 places, a transition from 0 to 1 or from 1 to 0, and cannot be 0 everywhere. A reflectance function with more than 2 transition places do not give rise to any new color. This is even true for other modulations of a full spectrum. Any color can be shown to be chromatically equivalent with some ideal color under a given illumination. This means that the system of ideal colors is all-embracing. Schrödinger further showed that the ideal colors are optimal in that they are the brightest among all chromatically equivalent ones. Let me show you an example. First, you have a reflectance function following Newton's idea. Light sources in the blue region of the spectrum are reflected more copiously than the rest, resulting in a dark blue color. Below that, an ideal color is shown, constructed by carefully choosing the position and width of an absorption band. The resulting color, with the same hue and saturation, turns out to be considerably brighter. Apparently, inks and pigments approximating ideal colors are the most energy-effective ones and desirable for painting and color reproduction purposes. So Newton should preferably have proposed colors in the object are nothing but a disposition to absorb this or that sort of rays more copiously than the rest. Working in a dark laboratory, he probably never considered the fact that under ordinary conditions full brightness is given and the colors are due to selective darkening. Darkness plays the decisive role when it comes to object colors. Whereas the ideal colors span a 2-dimensional set of possible variations, transmittance and reflectance in practice can be found in infinitely many variations. Does this mean that they lead to a more comprehensive color world? In a sense, yes, but according to Schrödinger's analysis, any color you find can be visually matched with one among the ideal colors, under condition that you are allowed to compensate for the fact that the real color may be considerably darker than the corresponding ideal color. Thus, any color you observe in the world around has a visual equivalent among the ideal colors, but usually with an excess of darkness, or blackness if you like, when seen among diverse other colors under one and the same illumination. This gives rise to color qualities described as earth colors, brown, olive, etc., and even grey. It is an astonishing but logical fact that there is no place for any grayscale in the world of ideal colors. What is so exciting with ideal colors is that they exclusively have to do with the periodicity property of light, that is to say, what wavelengths or frequencies are to be found or not to be found in a beam of light. The intensity and the periodicity of light are essentially independent dimensions. Modulation of the intensity is what we experience as a play of light and shadow in practical situations, informing us about other things, about the positions and shapes of objects. The wavelength composition informs us about the inner nature of matter, since it is related to atomic and molecular structure. Moreover, it is translation invariant, which means that the spectral composition even may inform us about the constitution of distant astronomical objects. Thank you.